Hello and welcome. Today we will discuss Hume-Rothery rules. These rules pertain to formation of continuous or complete solid solubility in solid solutions. In the last lecture we were discussing solid solutions and we saw that we have two kinds of solid solutions, interstitial solid solution and substitutional solid solution. Interstitial and substitutional. We also saw that in some solid solutions, so let us see, some solid solutions have solubility limit. Solubility limit, meaning that there is a maximum amount of solute, there is a fixed maximum amount of solute which can be introduced into the solvent. So, there is an upper limit. Upper limit on solute content in the solution. But we saw that there are two types of solutions, some solutions show this upper limit. So, for example, carbon in gamma iron, which we call austenite, or zinc in copper, which we call alpha brass. These solutions have a solubility limit. That is, only a maximum amount of carbon can go into gamma iron and a maximum amount of copper or zinc can go in each other, maximum amount of zinc can go in copper. So, that is what is our alpha brass. So, there is an upper limit, but in some cases, so another example is, let us say copper and nickel. This pair of element can be dissolved or can be mixed with each other in any ratio. I can make solid solutions starting from pure copper right up to pure nickel in any proportion. So, they do not exhibit any upper limit. Solubility do not exhibit solubility limit, or in other words, it is also called that they form an extensive or complete solid solubility. And Hume-Rothery rule, and in today's this lecture we will address this question, that why is this difference between these two kinds of solid solution, that some have an upper limit on the solute, exhibit solid solubility limit, form so called saturated solid solution, whereas there is no such saturation if I am mixing copper and nickel, I can do it in any amount. So, let us first look at two types of solid solution, interstitial and substitutional. So, first let us look at the interstitial solid solution, and let me start with this two dimensional cartoon example, and let me call this pure A. So, the first diagram is representing pure A, and now I want to make an interstitial solid solution by adding B to A, and B of course, as we have seen in the previous lecture, will go in the interstitial voids of A. So, these are the location of interstitial void. So, I place 1 B here. Of course, there are other voids empty. So, I can put one more. Of course, I can continue this process and ultimately I will fill all the voids. And once I have done that, I have automatically found an upper saturation limit. Beyond this, I can't put any more solute. So, we can call this a solid solution all voids filled. This is also solid solution, but only some voids are filled. So, we can see that there is a geometrical upper limit. Once all voids are filled, it cannot accept any more solute. So, this I will call a geometrical limit of solubility. Solubility in interstitial solutions solution. This happens when all voids are full. So, obviously, interstitial solid solutions cannot show the kind of unlimited solid solubility which we were mentioning. So, we note that interstitial solid solutions cannot exhibit unlimited solid solubility. There has to be an upper limit. When all voids are full, the solution has to be saturated and nothing more can be done beyond that. Let us look at a real example, that was a cartoon 2D example, a real example of a solid solution of carbon in gamma ion. This is austenite. The name of this solid solution in particular is austenite, and let us look at what is the real situation in this. So, we have gamma ion which is CCP, and carbon goes in octahedral void. This is known from experiments that carbon goes in octahedral void. Now, the question is how many octahedral voids are there in CCP of iron? We have done this exercise before, and if you recall, there is one octahedral void per atom in CCP. So, this means there is one octahedral void per iron atom in gamma. In CCP gamma ion, there is one octahedral void per iron atom, and suppose in the geometrical limit we fill all these octahedral voids. All voids filled. This will give us 1 carbon atom per iron atom, which of course, in percentage you can see that this is a 50%, 50 atom percent, 50 atom percent carbon in iron. So, the 50 atom percent carbon in iron will be the upper geometrical limit in CCP iron. You cannot put more than that. In reality, of course, you will see that this solubility is limited even further. So, if we look at a real case for the gamma ion, we find that the maximum solubility actually is limited only to 4 weight percent. Maximum solubility of gamma iron of carbon in gamma iron is only about 4 weight percent. And if you converted this into atomic percent, you get this to be 16 atomic percent. So, although you had 50 atomic percent as the upper geometrical limit, in reality it is only 16 atomic percent. So, the real limit, the real upper limit, experimentally observed upper limit is much less than the geometrical limit. So, there may be other factor which might be controlling this solubility. So, what is that other factor? So, that other factor is a strain caused by the solute atoms. So, if we look at the size of the carbon atom, radius of the carbon atom has to fit in the octahedral void. So, let us say that the carbon atom radius is R carbon and iron atom radius is R iron. These are radii of carbon and iron. And now, we know that octahedral void will give you an accommodation for a maximum size. So, R octahedral which is root 2 minus 1 times the radius of atoms, in this case the iron atoms, which is about 0.41 for R iron. So, the carbon atom has to fit into this void which can accommodate at most 41% of the radius of iron atom. But the actual size, although carbon atom is smaller than iron atom, but it is larger than the void size. And this misfit causes a strain. Causes displacement of surrounding atoms, which we say is a strain. Strain in the matrix. So, as more and more solute dissolve, more and more of this strain will come, thus the strain energy of the system will increase. This increasing strain energy is what causes an upper limit, a physical upper limit of the solubility. Solution energy increases with solute this finally gives an upper limit to the solubility. Now, let us look at the substitutional solid solution. So, in interstitial case we saw that there is a maximum upper geometrical limit which cannot be exceeded, and in reality the real limit may be even less than the geometrical limit, and usually it is much less than the geometrical limit, as we saw in the case of carbon in iron, and that is because of the misfitting. The atoms do not fit exactly in the void and causes strain. What is the situation in substitutional solution? So, let us start with this substitutional solid solution. Again I have this cartoon diagram where I start with this pure A. This is my pure A, and then I start making solution by substituting. Now, I am not putting the next atom in the void, I am substituting A is sum of A by B. So, let me substitute this central A by B. So, I have got a solid solution A plus B. Solid solution A plus B, and I can increase amount of solute by substituting more. So, in the last figure I had already substituted for the central atom. Let me substitute some more atoms. So, I have increased the concentration of B, and if I continue this process, if I substitute all of them, at least there is no geometrical constraint, one by one I can keep substituting all the A atoms by the B atoms. So, instead of pure A, I get to pure B. So, unlike all voids filling leading to an upper geometrical limit, there is no such geometrical limit in the substitutional solid solution. I can, at least in principle, substitute all the atoms and get to pure B. So, the conclusion is that unlike interstitial solution, there is no geometrical solubility limit for substitutional solution. So, this is an important difference between interstitial and substitutional solid solution, and we have already seen an example that if we take this, if I take A as copper and B as nickel. So, I have a real life example of two elements which do just this. I can mix them in any proportion, I can start with pure A and go to pure B, making solutions of different concentrations, and all those solutions are possible. So, it is geometrically possible, and there are examples of this also, but not all substitutional solutions do this, and we have example of this also. We have already seen that in alpha brass there is limited solubility of zinc in copper. whereas we saw in copper nickel we have unlimited solubility of nickel and copper. So, this is the situation for interstitial solid solution, unlimited solid solubility is not possible. For substitutional solid solution, unlimited solid solubility is not ruled out by geometry, but still physically some form unlimited solid solution, copper and nickel being example, and some do not. So, this was an important question, and this is the question which Professor Hume-Rothery of Oxford University tried to address, and we call them as Hume-Rothery rules. So, we now come to Hume-Rothery rules. These are empirical rule. What Professor Hume-Rothery did was to look at various substitutional solid solution and various factors related to them and try to correlate them with the solubility of those elements. And based on that, he found these empirical or experience based or experimental based rules. So, these are not strict rules, they can be violated, but they do give us a guideline or guidance regarding the solubility limits. So, let us again start with our two dimensional cartoon example, and we just saw that if we start with pure A, if I start with pure A and start substituting B for A, so I start getting A plus B, and if I substitute all of them, I get pure B. So, in terms of composition, I can go from 0% B to 100% B. If this is to happen, so we start we were here 0% B, which is pure A, and this is 100% B, which obviously is pure B. So, from pure A we are going to pure B. If we do this, remember, if we started with some crystal structure, let us say pure A is cubic close packed. So, on the cubic close packed sites, I am replacing B for A one by one. So, the end result, the pure B which I will get also has to be CCP. So, if we have complete solid solubility system like copper nickel, the two crystal structures have to be the same. So, the conclusion is crystal structure of solute and solvent. In this case anyway, distinction also is not immediately obvious, because they can be mixed in any proportion. So, crystal structure of the two elements should be the same. We saw that alpha brass does not form complete solid solubility. So, if we look at alpha brass again, alpha brass, we have copper, copper is CCP, but the other element is zinc, which is HCP. So, obviously, complete solid solubility is not possible because structures are not the same. So, we will say structure factor is not favorable for solid solubility. Otherwise, if I start replacing for copper one by one zinc, then finally, I will end up with cubic close packed zinc, but the zinc structure is hexagonal close packed. So, complete solid solubility not possible. Not possible. So, we now go to the next factor, the size factor. Now, structures may be same, but still a complete solid solubility may not always be possible. So, there is another factor which is the size factor, and we have already seen the effect of size in interstitial solid solution. The same effect of size comes here also, that when two elements are widely different in size, they will cause lot of strain, limiting the solubility. So, what Hume-Rothery found by experimentally studying various systems. So, he found that complete solid solubility is exhibited by a pair of elements having a size difference we should call this atomic size difference. We are having an atomic size difference of less than 15%. So, if the size difference is more than 15%, it is less likely that they will form a complete solid solubility. Let us go back to our example of copper and nickel. So, copper, the radius of copper atom is 1.28 angstrom, and the next element is nickel, and the radius of nickel atom is 1.25 angstrom. So, we can see that the size difference delta r in this case is only 0.03 angstrom, and if we try to find the percentage size difference, this comes out to be about 2.4%. So, you can see that 2.4% is much less than the 15% specified by Hume-Rothery. So, we expect that they should form a complete solid solution, and in this case it is true also. Of course, these rules are provisional, and it is not necessary that if the size difference is within 15% they have to form. There are counter examples known, but this is a guideline for this kind of solid solutions. Finally, two more rules are there, and I am putting them together: electronegativity factor and valency factor. Again, by experience, Hume-Rothery found that for complete solid solubility, electronegativity, so let me write down, for complete electronegativities and valencies of the elements should be close. because what he found that if the difference is too large, if the electronegativity difference or valency difference is too large, so there is more likelihood of formation of compound rather than solid solution. So, large difference in electronegativity or valency indicate a tendency towards formation of compounds. So, with this we complete this Hume-Rothery rules. So, we have now discussed a structure of metals, the close packed elements, the cubic close packed, hexagonal close packed and body centered cubic metals, and then we also discussed the voids in those metals, and then when the voids are filled we get solutions, interstitial solutions, and when atoms are substituted we get substitutional solid solution, and then in today's class we discussed the difference between complete solid solubility and limited solid solubility and the pertaining Hume-Rothery rules. So, with this more or less we have discussed the structure of metals, and in the next video maybe we will take up the structure of carbon, which is an inorganic material carbon, and later on we will look at the structure of some non crystalline material